Since the beginning of time,
New strain of virus.
man has been at odds with the forces of nature.
3, 2, 1, and liftoff of the Cassini spacecraft on a 30-mile trek to Saturn. Which program is in?
Hello and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. And our special preview of Cassini's grand finale.
How many people from this title have an idea of what we're going to be talking about tonight? Show of hands. Most of you, but some don't have a clue.
I guess one way to look at today is the day of challenge, where we're going to be challenged by our new views of Saturn. I think it's fair to say that everything we're seeing today, basically everything we're seeing today, will be new.
You know, in 1610, Galileo, with his very primitive telescope, observed Saturn for the very first time.
Cassini was named for the 17th century astronomer Jean-Dominique Cassini. Here in the Paris Observatory, he discovered 4 of Saturn's moons and the division in Saturn's rings.
Cassini was Italian, but Louis XIV invited him to come here, and he discovered 4 satellites of Saturn. Here you can see the notes by Cassini, where he put discoveries.
The spacecraft Cassini will orbit Saturn for at least 3 years, giving scientists an extended look at the ringed planet and its elaborate system of moons.
This thing was launched back in 1997, okay? And you can think about it, it was designed and constructed before that, so we've got, what, over 20-year-old electronics in there. You know, your iPhone 4 can do better computing than this thing can do, but that's what we had 20-some-odd years ago.
There's no way that I can tell you everything that we have found in that time, or show you all the beautiful scenery and vistas that we have come to see. So I'm just going to show you some of the highlights, and I think these are the highlights that convey just how profoundly successful this mission has been.
Cassini will tell us in detail what the most interesting scientific questions are for the next phase of exploration. Many of us believe, of course, Titan will be among those questions, but the Huygens probe and the data from the orbiter will help us better define what it is we want to do when we return to Titan.
We received several pictures yesterday afternoon and evening, and we'd like to run through some of those now. This is the one that came in here at about 3 o'clock yesterday afternoon. This is raw data. It has not been processed in any way. What we're seeing there is a portion of the cloud tops at Saturn near the equator.
Photographs show what appear to be jet streams swirling around Saturn at 300 miles an hour, a new ring circling the planet's equator, and radiation belts that are more like Earth's in their intensity and energy levels.
The planet appears oblate. It is oblate. The diameter quite a bit larger at the equator than it is down through the poles.
But the pictures did not have enough resolution to show the planet's rings and moons as clearly as the later Voyager pictures did.
These computer-generated pictures show what Voyager 1 will see, traveling toward its closest encounter on November 12th. It should reveal some exciting discoveries about Saturn which have been beyond our grasp.
An outer space spectacular that was the stuff of dreams only a generation ago began snapping into the sharp focus of reality today. After its billion-mile journey from Earth, the Voyager 1 spacecraft sent back pictures of man's closest look yet at the ringed planet Saturn.
Saturn's composition has been a scientific puzzle because of the dense clouds. Voyager has returned more than 18,000 photographs. Photographs that are giving scientists excellent close-up views and new information about the huge planet and its many moons.
Voyager 2 produced thousands of pictures of Saturn and its rings and moons from different angles and distances than did the first Voyager spacecraft.
High-resolution photographs of the planet and satellites are assembled from mosaics of images covering separate areas of each target.
Our next clip from September 1981 shows us some of the Voyager 2 results from Saturn.
Those music-like sounds are actually radio waves picked up by the plasma wave detector on NASA's Voyager 2 spacecraft as it approached and swept by the planet Saturn. Voyager 2 passed within 63,000 miles of the many-colored planet and transmitted back thousands of extremely clear pictures. Astronomers were surprised at the complexity of Saturn's rings.
Hi, Ted. Well, the latest is that we have just made the closest approach to Saturn. The spacecraft is now recording data, which it will send back to us at a later time. There's a whole suite of observations to be made after we pass Saturn. There are moons that will be observed close up. For example, Enceladus is a moon which in the next few hours we will have the closest approach to.
Carl, let me interrupt with a question that lets me be as ignorant as I am on this subject. You clearly believe, you know that you have made a quantum leap, and you have just taken us through that quantum leap. But why? The pictures don't look all that different.
Well, the picture we just saw, in which there were huge numbers of rings, is quite different from the picture before that, a typical ground-based photograph, which shows maybe 2 or 3 rings. The existence of 1,000 separate rings, which are produced by satellites near and in the rings, we think, is indeed a quantum leap.
We have a figure of the interior. This is built up by an inner core. I guess I have no control over how fast this accumulates, so we can let it go all the way out to the surface. But anyway, that inner core you see is made up of molten rock and iron. This model that we show here is essentially correct.
I'm thrilled to be able to tell you this afternoon, to take you, show you how this particular leg of this voyage, this grand voyage, through the Saturn system, as Cassini is revealing it to us, is how Saturn and everything around it has been shown to us.
The sunlight at Saturn is 1% as bright as it is here at Earth. And if you do photography, you'll appreciate, oh, it's going to make it harder to take pictures out there at Saturn. But they have been taking thousands of pictures since 2004.
Since I'm a radio man, I'm kind of fascinated with the radio system of the Pioneer and the DSN. And I'm very impressed by the fact that all of these data are received from a distance of just about exactly 1 billion miles. At this distance, if you are transmitting 1,024 bits per second, at any given time there are 5.5 million of those bits strung between here and Saturn, traveling at the speed of light, 5.5 million. And they're spaced 182 miles apart. With that, I'll quit.
How long does it take for an image to get from Cassini to Earth, like to get the data here? And my iPhone, I think, has 8 megapixels. What's Cassini have?
1 megapixel.
1.
And it's black and white.
We know how to convert that into a brightness. It tells us how much light is coming from that pixel. And that's calibration. And so we know that, and then we do that in several filters to make a color picture. If you're making a natural color, we choose blue, green, and red. We composite them together. We know pretty much how the balance goes between those three, although we don't really know it to a really high degree of accuracy, so there's always some, mushiness about just exactly what true color is. I could never promise you that something was exactly true color, but that's how you do it, just to make a pretty picture. Titan was, in some sense, a disappointment with the Voyager missions because the absorbing and scattering processes of the Titan atmosphere were exactly mismatched to the capabilities of the Voyager camera. Where the Voyager cameras were cutting out in sensitivity as you go to longer wavelength, that's where it turns out you could stand a chance of seeing down to the surface of Titan in the near infrared if you knew what spectral regions to look at, what spectral windows to look in. So between the end of Voyager and getting Cassini rolling, people copped on to this, that there were spectral windows you could actually see down to the surface of Titan, and we equipped our cameras with those filters.
We colorize our images with filters, and it takes anywhere from an hour to 90 minutes for the image to get from Cassini here to the Earth.
Whole megapixel image to...
Well, the megapixel, let's see, we do 140 kilobits per second.
Okay.
So it'd take 10 seconds or so, roughly, let's say 20 counting overhead, to get an image down here once it starts. But Saturn is an hour and a half light time away. So when Cassini starts to send a signal, her bits don't get to the ground for an hour and a half.
For an hour and a half.
Yeah.
Gotcha.
And so when we want to signal, send something to Cassini and have it answer, we have to wait anywhere from 2 to 3 hours. Yeah.
Wow.
It just means Cassini has to be very smart. She has to basically have commands on board to keep her going, typically for 10 weeks at a time. Where to point, where to look, when to send data back. And so very, very smart spacecraft.
The type of image processing? It depends for what purpose. I mean, if you're talking about just making beautiful images, we have to work with calibrated images, so we know how to calibrate. We've spent a lot of effort to learn how the instrument responds and how we take the number that comes out of the camera, so to speak. We just call it a data number. It could be 4.
The pictures were converted to an electronic number code, and the numbers were transmitted to Earth via radio waves. Computers then use the numbers to reconstruct the images.
The suite of instruments being carried that are on the Cassini spacecraft is the most sophisticated suite of instruments ever taken certainly to the outer solar system. It's remarkable. I mean, we started with Voyager. I think there was one computer for operating all, whatever it was, 8 instruments. But we have 12 scientific investigations on the orbiter alone. And each of them has sub-investigations, like the imaging investigation has 2 cameras. Each of them has their own microprocessor, and it's so many more capabilities built into the Cassini spacecraft that makes our job, a lot easier.
So what's the data rate back to Earth, and do you have to buffer the images on the spacecraft?
Oh yeah, we have to buffer, and I don't remember the data rate. Isn't that ridiculous? But I don't remember. I don't even want to say because I'll guess and I'll get it wrong, and this is being filmed and it'll go out there and I'll forever be wrong, so I won't say it.
I did have a question about the temperature. It's so damn cold out there, and I'm wondering, for 14 years, Cassini's been performing and doing things.
Well, it has
fairly actively. I'm wondering, is the cold a hindrance or a huge challenge, or is it actually like a preservative that keeps things in order when they're...
The thermal part of spacecraft design is, as far as I could tell, I'm not a spacecraft engineer, but I've been around them for a long time. That's the most challenging part. Thermal gradients just screw everything up. So you want to reduce thermal gradients. I don't think it's so much the temperature, but it's gradients.
Oh, wow. It's cold at Saturn, let me just tell you that. So Saturn's a very cold place, and one of the things that's involved on the spacecraft team is we have all these subsystems, right? So there's a thermal subsystem that actually studies all of these temperatures, and they have heaters, they have all these blankets that are on the spacecraft that's really to protect our instruments, because everything there is frozen. So water there would be frozen, so it's cold.
I don't really get my jollies, building or thinking about instruments, but I have to say we had just a really lovely collaborative effort in building the cameras, and it shows. They work phenomenally well. Across from the front to the back of the camera was a terrible thing because then it screws up. It's a long focal length camera. I mean, it's folded, but still. you get distortion because of that thermal gradient. So we have heaters in the cameras that reduce the gradient or try to keep it stable.
Well, okay, like the cameras. Let me describe the Cassini cameras. They're the most sophisticated cameras. In fact, Cassini's payload is the most sophisticated payload that was ever taken into the outer solar system. In our cameras, we have 2 of them. We call them cameras. They're actually telescopes. And outfitted with many spectral filters. That's why Cuneo can look at the hexagon and all sorts of different spectral filters, and they kind of slice the Saturn atmosphere and give us a shot at different levels in the atmosphere. Other images, like the one our mosaic is made of, this particular mosaic, whereas our red, green, and blue, we can use those to make what you might call natural color, but they also have scientific purposes.
Our cameras have 2 filter wheels. Essentially you can take a green, blue, and magenta filter, not magenta, blue, green, and well, whatever the 3 colors you pick, and colorize them, right? It has infrared filters that penetrate the haze. And so each of these filter wheels, you actually rotate that filter into the image path and take an image, then rotate another filter, take another image, and they're combined and colorized on the ground.
So the colors you end up with represent what you're actually looking at, or is it?
They can, or they can represent some of the false colors that you've seen, like the red hurricanes and things like that, that accentuate levels of elevation or of chemical constituents.
Okay.
A lot of the pictures you've seen were natural, but some of the others were false colored to highlight whatever meteorological or chemical item you're trying to look at.
But you can get true color. You take those filters and add them together in different ways, and you get the true color that you would see with your eyes in those pictures.
This is produced in false color because it gives us a little more contrast to the features that we're looking at. The colors that go into this are ultraviolet, violet, and green.
And then there's many other capabilities in the cameras I don't have the time to go into, but I will tell you, first you need to know, if you ask this this question of any planetary scientist, you'd get a different answer probably from each one. So we're not so much in the business of identifying whether or not it's, well, I can't even guess right now, but we're not identifying particular chemicals or chemical bonds. What we can do is we can say that we have an ice on the surface that absorbs a lot in the infrared, but maybe not so much in the ultraviolet. In some sense, colors is really the spectral information that we can get with the cameras.
Rather than have a picture that's got, let's say, Enceladus looking blue, green, red, we deliberately, composite them. So we cheat a little bit, and we, take the 3 images, put them on top of one another, and put it in the final image. But that's for just public release. I mean, there's lots of things we do to extract scientific information. I could bore you with it for hours. I mean, so.
So anyway, I'm going to begin this lecture with the story. And it's a remarkable story about the inhabitants of a rocky little ocean-covered world in orbit around an ordinary star,
one of hundreds of billions of stars in an ordinary galaxy,
in a universe filled with 100 billion galaxies.
The story of Cassini,
has been at its heart a story about longing.
A longing to a story about longing.
Know ourselves.
A longing to understand us.
And how we got here and where we has been at its heart.
And it's a tale about
the longing to understand us.
To know ourselves.
I'm going to begin like the stories of all of our interplanetary missions. In the end, the story of Cassini,
a longing to know ourselves
and how we got here and where we came from. Where did all of this come from?
The longing to understand us.
And despite all the beautiful scenes and images that we have seen over the last dozen years from Cassini,
there is an image that speaks of this longing.
There is one image that speaks of this longing
So much better than words ever could.
better than any other, and even better than words could.
Well, I have, I think, the best job of everybody here, because I get to tell you about this fabulous and unusual event that occurred on July 19th, an event we call the Day the Earth Smiled, on which we took the Cassini cameras and turned them in the direction of Saturn and the Earth and took a big glorious day.
Why don't we tell people ahead of time? On such and such a date, such and such a time, your picture is going to be taken from 1 billion miles away, from an orbit around Saturn. And why don't we invite them at the appropriate time to go out, to contemplate the utter isolation of our planet in the blackness of space. And so it happened. On July 19, 2013, 2 years ago, the Cassini cameras were turned to look at Saturn while it eclipsed the sun.
And we sent out the word ahead of time. Get out there, feel the cosmic love.
Straighten up, comb your hair, go out, look up, think about all of us together on this pale blue dot. Many comments came in from people all over the world describing a feeling of unity with their fellow humans, and here are just a few that I want to read to you because they're precious. We've got a lot of them, but these are ones that I culled out. So this is from Sam. Phoebe, age 10, and I got the telescope out on the patio. Under a beautiful, clear, southern British sky,
we gazed upon Saturn, reveling in the fact that a spacecraft was looking back on us.
She asked lots of questions about Saturn, and at the appropriate time, I raised a glass of fine red wine, she a glass of fizzy pop. We said, cheers to Saturn, to Cassini.
To each other, then we smiled
and laughed
and waved,
cheered and laughed, smiled and waved, and we smiled, laughed, and took photos of ourselves both beaming. It was perfect.
At the appropriate time.
Right there, right at that moment. This is Tess, somewhere I don't know. This experience was beyond meaningful. I left the table at a restaurant.
Right at that moment.
What a beautiful thing.
At the appropriate time, I turned my face to the sky.
What a feeling of connection and oneness with the miracle that is life on Earth.
Watching and listening to what life on Earth was like.
What a feeling of connection.
It was transcendent. What a beautiful thing.
This experience was beyond meaningful.
It was 4:27 p.m. in Houghton, Tennessee.
From Lake Ontario.
We went down to the waterfront and threw a wave in a general upward direction. Spent a few minutes.
And I went to the parking lot.
What a feeling of connection and oneness with the miracle that is life. I don't exactly know where she was, but anyway.
Watching and listening right there, right at that moment. This experience was beyond meaningful. It was transcendent.
I left the table at a restaurant.
Right there.
I turned my face to the sky.
Listening to what life on Earth was like. Right there, right at that moment. What a feeling of connection.
And Tess from somewhere I don't know where.
My daughter and I hung a home sign.
However, I never anticipated how emotional I would feel.
Watching and listening to what life on Earth was like.
I stood on the edge of Lake Ontario.
It was transcendent. What a beautiful thing.
I turned my face to the sky and I spent a few minutes.
And oneness with the miracle that is life on Earth.
Ever since I heard about it and was determined to join in the celebration.
This is Chris.
I had been entranced.
This is Jolyn.
I stood on the edge of Lake Ontario.
We smiled for the camera.
So in the end, we just spun in circles, waving at the sky. I was in Reykjavik, Iceland.
I have been entranced by this project.
It was transcendent. What a beautiful thing.
Phil in Tennessee.
Just incredible. This is from Jolyn, somewhere in upstate New York. I was determined to join in the celebration. I've been entranced. I stood on the edge of Lake Ontario in upstate New York with my son and his girlfriend.
I just never knew how emotional I would feel.
So in the end, we just spun in circles, waving at the sky.
The thought that a camera was taking pictures from so very far away was just incredible. We may not be unique, we may be transient, we may be only flying along in a dust mote.
But darn it, for those 15 minutes, we were there, we were where, and we smiled.
And here now is the mosaic. I'm sure many of you have seen it. That was taken as these people and many more all over the globe were thinking about our cosmic place and smiling in the sheer joy of being alive. A picture of a sight that no human had ever seen before, a total eclipse of the sun in which we can spot across 1 billion miles of interplanetary space our own planet Earth, cradled in the arms of Saturn's rings. I've called it the day the Earth smiled. And it shows Saturn eclipsing the sun. It shows the main rings lit from behind so they look as if they glow. And it shows, in fact, the lovely blue ring that is, in fact, the result of the spray from those 100 geysers erupting from Enceladus. And if you look closely, over the shoulder of Saturn, 1 billion miles in the distance, you will find our home planet Earth, which when looked at with even higher resolution, with our high-resolution cameras, becomes the Earth and its moon seen for the first time from the outer solar system.
You have seen it on, I bet, no doubt. This is Saturn eclipsing the sun as we had planned because we couldn't look directly into the sun or we would have ruined the cameras.
And looking over the shoulder of Saturn in the distance, 1 billion miles in the distance, is our small little planet Earth.
The data from the Voyager 2 Saturn encounter are still being analyzed by scientists.
And when examined even closer with our high-resolution camera on Cassini, becomes the Earth and the Moon.
There is something incredibly powerful that we feel when we see sight of our own fragile, blue, ocean-covered little world as it would be seen by others in the skies of other worlds. And I think that it is that startling and uncorrupted recognition of ourselves as we are, where we are, that never fails to move us. And it moves me to think about evolution. In fact, for me, this is the picture where the Italian astronomer Galileo and the English biologist Charles Darwin come face to face.
Because it is a picture that was ultimately made possible by Galileo's first experiments with gravitation over 400 years ago, and it is a picture that absolutely shouts evolution.
One of my favorite pictures, and I think the most stunning, is the backlit Saturn. That picture where Saturn is covering up the sun, and you see the rings blazing in all of their glory. You see actually a ring of light around the planet as the sunlight refracts through the atmosphere, and it's just not only a stunning picture scientifically, but also very beautiful. And if you look carefully, you'll find the Earth, Mars, and Venus in that picture as well.
That's my favorite one too. It's the background on my laptop. So
let's look at that image in a very different way. And what you see when it comes up is this is a collage that includes 1,600 images that were sent by members of the public to us as part of Cassini's Wave at Saturn campaign.
And we've come to know this planetary system that is 10 times farther from the sun than the Earth, okay? And we've come to know it intimately. And the best way I could underscore to, the uninformed or the layperson as to how far we've come, all they have to do is take a telescope like the one you looked through when I was a teenager on the roof of my friend's house and look at Saturn and then go look on our website at one of our pictures. And that's how far we've come.
Are these images available on the web?
Oh, yeah.
Can you tell me the web address?
Okay. So our website is cyclops.org, CICLOPS.org. It's an acronym. I learned how to do acronyms from JPL. Cassini Imaging Central Laboratory for...
Cyclops.org. Cyclops.org. It stands for Cassini Imaging Central Laboratory for Operations, OPS. CICLOPS.org. That's where we post all the images that we take with our cameras.
We've got web pages everywhere. We've got our raw image site, which we publish every image that we get the minute we get it on our site. They're on the social media before we see them. I'll come in the morning and the Twitterverse is already alive with our images, which is just so cool. I love it.
They have all kinds of fantastic information. Not data, well, they also have all this great data about what the environments are like, but what you really have to check out are the photos. The images are just incredible. Up-close views of Saturn that are going to continue to get better over these next 22 orbits as we head towards the final dive on September 15th. But also throughout the entire mission, the photographs of the moons, the photographs of Saturn, the photographs of Earth from Saturn. Oh, there's a great photo I saw just recently that Cassini took looking back to Earth from Saturn's distance out in the gap between the rings and the planet itself. Boy, talk about giving you a good perspective on our little planet here.
Can you turn the spacecraft around so you can see Earth again before the end of the mission?
That's a great question. Yeah, so we actually turn to Earth a lot. That's how we communicate with the spacecraft. So this antenna isn't just a shield, it's actually an antenna, so we can communicate with the Earth. So we have antennas on the spacecraft, we also have antennas at the Earth. So there's pictures up here of 3 different stations that are located around the Earth. There's one in California, one in Spain, and one in Australia. And when we turn the spacecraft to Earth point, that's actually when we can communicate with the spacecraft. We can downlink data and receive data from the spacecraft, or we can send up commands so that they're loaded onto the spacecraft so it can turn around as much as they want. So we turn to Earth a lot, actually.
Right, but as far as taking pictures of the Earth, that's much harder to do. And we've done that for the last time before these ring grazing orbits. You have to get at a special orientation where Cassini is in a place that Saturn covers up the sun. Then you can look close enough to Saturn and not damage our sensitive cameras and get pictures. In fact, we have this beautiful mosaic, one of my favorite pictures, that if you look carefully, there's the Earth and the Moon, and then Mars and Venus, all in this same mosaic of pictures.
It's a really great picture. It's one of my favorites, yeah.
Probably one of our most famous from the whole mission.
Hi. So I will be talking about the images we are releasing today of Saturn's hexagon, and so we are looking at Saturn from Cassini spacecraft's vantage point, which is in orbit around Saturn since 2004. So I have been studying this feature called the hexagon around North Pole of Saturn. The feature is not new. Just to be sure, we've known that it existed since at least since '81, and we confirmed that as soon as Cassini went into orbit around Saturn. It was still active in 2004. I think we're still waiting for the image. So we are in orbit around Saturn. The images we're releasing today, let's see, the image that just showed up is how Saturn's north polar area looks like from orbit of Saturn. So right in the middle is north pole of Saturn, the darker spot, and then you can see the clear geometric hexagon, geometric shape, which has 6 sides and corners. That's why we've been calling it the hexagon.
Saturn also has something very unusual. It has a hurricane at its north pole, but that hurricane has a hexagon shape. So rotating at about 77 degrees north latitude is a 6-sided hexagon. Why it keeps those straight sides, we really have no good idea.
Put anything on our website having to do with the hexagon, the hits go through the roof. People just can't get their head around things with straight sides in an atmosphere, and they think this is, I don't know, some kind of crystal energy. I don't really know.
But anyway, there's nothing peculiar about the hexagon. In fact, I've encouraged people not to even call it the hexagon anymore. And you can tell all your friends that too. There's nothing to get weird about.
So my apologies to the New Age people, but you can quit praying to it. And surely one of the most beautiful images that we in my shops, my Cyclops back in Boulder, where we process most of the images that we release to the public, one of the most spectacular ones is this. And it was so beautiful, it was considered so beautiful and made it all the way to the nightly news. Brian Williams talked it up.
Here's the hexagon. This was early on in 2006, again with infrared light. They just colored the picture pinkish. When you look closely, you see a regular six-sided hexagon right around the North Pole. What that?
And there's this gigantic hexagon. It's still there, still whirling around the North Pole. And one of the things that we've also found is that the clouds inside that hexagon also move around at around 300 miles an hour.
So the spacecraft has actually discovered a tremendous amount about Saturn, understanding the magnetic fields of Saturn, understanding what the atmosphere is like, and particularly looking at the really dynamic atmosphere of Saturn, where all kinds of really great things have been discovered. So for example, did you know that Saturn is a planet that has its own aurora? You may not have known that, but yes, it does. Right at the north and the south poles, it has auroral activity that has been photographed in ultraviolet light.
Now somebody was very bright. They said, well guys, yeah, it's 2006, it's dark up there, but just for the heck of it, why don't we turn on the visible light camera too in addition to the infrared? And they did. It doesn't cost any more. Aurora. Here's the hex. Do you see the hex? Here is aurora, just like we have at the north and south poles of Earth.
The way the winds work at Saturn, particularly at the poles, you can actually see that there's an interesting hexagonal shape to the clouds right around that polar region. That's extraordinarily unusual and was completely unexpected to be found there.
So I said that the hexagon around the North Pole of Saturn is a meandering jet. So the meandering property really depends on the details of the jet. So the jet around North Pole has the right speed and the width to have to fit in a wave, basically to fold into six-sided shape.
Now we had some idea, of course, how the clouds, as they circulate the planet, might cause various kinds of eddies and disturbances and all kinds of shapes called festoons, which are really clever, interesting little curly Q shapes that are developed as the clouds are sliding past each other at various velocities.
We're seeing material actually flowing out and forming rather curious patterns. Here is that high velocity jet showing somewhat of a Rossby-like structure, Rossby wave-like structure, and associated with it are some cyclonic, that is the equivalent of low pressure areas, in a system that's not altogether different from the Earth. This is...
And then, of course, we have a lot of vortices, but what we do have around Saturn's south pole is a hurricane-like structure that we do have in the North Pole. So there are similarities and differences.
We've always thought of Saturn being this serene body up there that it's very lovely. There's a few storms on it, but it looks very like a pearl in the sky with different hues to it due to different types of clouds, but nothing very dramatic. What we're seeing is that if you go through those hazes and get down to the depths of Saturn, you find a roiling atmosphere of all sorts of dynamical features going on, and the cyclone is probably one manifestation of this dramatic dynamics that's going on inside roiling Saturn.
So I think that major objective, once we do the detailed analysis of those storm systems, exactly how rapidly they're rotating, what their speeds are, and relate those to the high-speed jet streams, that we may have a very important piece of the story for the weather system on Saturn.
The sun is rising near the North Pole, the Arctic Circle of Saturn or whatever, and sure enough, several years later, our hexagon is still there, Now, of course, this is dark because light had not gotten all the way up to the North Pole when this picture was taken. I'm sure that this square thing is an artifact in the camera of some sort. We see these in a lot of their pictures. You may have already noticed some notches out.
It's definitely not an illusion of any kind. This is a real feature that does exist, and it has been there since 1981. It is gas, so it's clear. Well, it's a pattern of clouds, so it's gaseous. It's not a solid feature that we have on the surface of Saturn. Saturn is a gas giant planet, so there's no such thing as mountains and valleys or even oceans on Saturn. All we have is a bottomless atmosphere. If you try to land on Saturn, we're just going to sink to the core, basically, of the atmosphere. There's no solid ground we can stand on. But the hexagon is a real feature. It is a jet stream, as I said earlier. It is folded into six-sided shape, and it is a very stable feature. That is a surprising part of it, and we are studying that feature.
Saturn also has very interesting weather, according to imaging team leader Dr. Bradford A. Smith.
We, in fact, have found that there are similarities between the Saturnian weather and terrestrial weather.
We saw a giant storm, something that only happens once every 30 years, totally encircling the planet, and watched as that storm developed and is now dissipated.
So we can have huge storms that happen about once every 30 years around Saturn. We can have giant hurricanes at the north and south poles of Saturn, and can also have smaller vortices. There's a region we call Dragon Alley, early in the mission in the south, where we had lots of storms and lightning with it.
The closest, the largest storm ever observed from a close spacecraft, and the kind of storm that appears on Saturn every 20 or 30 years. Okay, so it was fabulous that we were there to see this thing be born, be developed, evolve, and then eventually die.
Yeah, so this is a very special kind of storm because Saturn is, of course, spherical.
The planet appears oblate. It is oblate. The diameter quite a bit larger at the equator than it is down through the poles.
But what's special about these storms is that it lasts so long and it's so big that it actually wraps around the planet. It's a single thunderstorm that blows up in one spot, but the cloud extends out so much. Saturn's a big planet to start with. On that big planet, this storm cloud completely wraps around the planet. So this is a very special kind of storm that actually wrap around the planet. Yay, there's the image. So this is, I think this is images from around February or March of 2011.
And then it grew over the course of just 2 months. It ended up wrapping itself all the way around the planet. And it was like lightning strikes, 10 times those of normal Saturnian storms, and lots of radio waves, thundering, basically.
So this was the 5th time we've seen a giant storm like this at Saturn. But what was unique is this storm was early. It had only been 20 years since the last storm, and so it came early so Cassini could get a good view of it and watch it. And so we watched it, as did ground-based observers. It lasted about 9 months and started to fade. It was a giant vortex, and that vortex swirled off this huge tail. The tail of the storm wrapped itself around the planet. There was another vortex on the other end, kind of like a hurricane. When these two vortices merged, that marked the end of the storm.
The pictures Voyager 2 sent back this morning were part of a sequence of photos shot 10 hours apart. Scientists were hoping they would show motion on the planet. Such motion would help them measure wind velocities and help them understand more about various weather conditions on Saturn.
Dark feature also on other clouds.
We can run it forwards and backwards.
If you stop it about there, Al, in fact, you can see that there are a large number of very bright patches in the region between about 20 and 40 degrees. And these are in the Northern Hemisphere. The large amount of detail is showing up there.
When it finally got dark enough at night, we pointed the cameras there, and wonder of wonders, there were lightning flashes, and took a series of pictures. And in one picture there'd be no lightning flash, and the next picture there'd be a lightning flash.
Well, there are, particularly at the higher latitudes, a large number of these small white features similar to many that we saw on Jupiter. They may be small convective elements, like a large aggregation of thunderheads or cumulus type clouds. The resolution was probably something in the order of 100 kilometers or so that gives you an idea of the scale of those features.
And at the same time, you hear the noise over the radio instrument.
And we actually saw it. I didn't believe it.
The lightning storms on Saturn are very much like lightning on Earth. You get the same strength lightning storms, or thunderstorms. They have the same strength, but they're just much less frequent. I'm enjoying the show.
Large bolts of lightning, as energetic as the total output of an Earth-based nuclear power plant, were detected in the Saturn B ring plane. Clouds in Saturn's atmosphere were clocked moving at speeds of 1,770 kilometers per hour.
Who use the computer to bring their imagination. Well.
Hi, thank you for your presentations. I have two questions here I want to ask. First is you guys said that the Cassini satellite, the Cassini drones, props, whatever, is the farthest from the solar system we have ever gone. Is it?
Oh no.
No. Well, what I said was that the Huygens probe landing on the surface of Titan is the furthest we've landed a probe on the surface. But the furthest spacecraft now away from the sun would be the Voyager spacecraft. They're well past the orbits of Neptune, Pluto. They're on out, even one of them into the interstellar wind. So
our 90-minute light time, they're a day and a half for a signal to get from the probe to Earth. So they're way out there.
I see.
I think that really makes people so excited about Titan is this combination of familiarity and alienness.
Titan, being at such a low temperature, has preserved those original conditions. So the kinds of chemical reactions taking place in Titan's atmosphere today, we think resemble the kinds of things that happened on the very early Earth, which ultimately led to the formation of life here.
And those moons or satellites, like outriders, they encircle Saturn, generating as much scientific interest as the great ringed planet itself. Mimas, Tethys, Dione, Rhea, Titan.
And the good news that Titan is there. The bad news is that we barely saw it. We were counting on, first of all, twice as much data because at the high telemetry rate. Secondly, we were counting on no data dropouts. So we have a good deal less data, and we're counting on lots of data in order to average it and beat down the noise. And I'd say we've said the temperature of Titan is 75 degrees Kelvin, plus or minus 5, which is about the temperature you'd expect for an object in equilibrium with the sun at that place in the solar system.
Maybe we can call up the Titan image, or one of the Titan images from last night. It doesn't have a lot of obvious features on it, I think you'll agree, but if you've heard the model builders talking, they haven't predicted a lot of obvious features.
This is the first view of Titan that we've released. It's a rather uninspiring orange ball, but there is this north-south demarcation with a line which still is in there fairly close to the equator of Titan.
Here is a lovely image of Titan, backlit by the sun, which is off to the left, and you can see the ring around it, which represents light which has been refracted through the atmosphere of Titan.
What we're after is what makes Titan tick. We want to know how it works. We have found that a lot of things on Titan are similar to what happens on Earth, with some big differences. It rains on Titan, but it doesn't rain water, it rains methane.
One thing about Titan, it is cold, okay? Titan orbits Saturn, which is 10 times the distance from the sun that Earth is. So what that means is you get a lot less flux from the sun falling on Titan than you do on the Earth. So the surface of Titan is about minus 290 degrees Fahrenheit. It's cold, right?
Actually, there have been some radio observations rather recently that show that the temperature at the surface is cold, not all that different from the temperature at the cloud tops. And this is sort of a suggestion that really the atmosphere isn't all that thick, and the cloud tops are not all that far above the surface.
Well, Titan is, of course, as everybody has been pointing out, one of the most fascinating places in the solar system. It's the largest unexplored chunk of territory that we know of in the solar system. And it may have characteristics very similar to the atmosphere and the chemistry that went on the early Earth.
So anyway, for all of these reasons, Cassini was deliberately equipped to the gills with instruments that could get to see down to the surface of Titan, something we couldn't do on Voyager. It did not have the proper equipment.
These purple lines here represent the radar beam as it sweeps across the moon and takes science. Now, all of the spacecraft movements shown in the simulation are using the real engineering data that I use every day to do my job.
We saw multiple images of the same place on Titan. We'd fly by one time, and then months later we'd fly by again. And we would see mountains had moved, lakes had moved, all these things had moved. And obviously they can't really move.
We see river terrains, fractures, we see basins, we see some highlands. We don't see huge mountains as we see on Earth. That's one thing that's missing. We see very few craters, and that's true for the Earth as well. So other than the absence of life and the fact that this is a much colder environment where liquid methane plays the role of liquid water on the Earth, the things that we see echo in a kind of a strange way what's seen on the Earth, and that's fascinating.
We could see in places it looked like there were channels, and of course we were expecting channels, and we thought we saw some, and we thought we saw things like maybe a few, very, very few craters. Anyway, we were having a very hard time seeing what was going on in Titan, and then, of course, came the Huygens probe.
We've carefully been targeting, crafting the trajectory to get it in a position to where we could finally release it, and tonight we broke it loose.
I was really spooked in early 2005 when the Huygens probe returned sound recordings from the surface of Titan. This is exactly what I described in my 1975 novel Imperial Earth, where my character is listening to the winds blowing over the desert plains. Perhaps that was a foretaste of things to come.
The winds of Titan as it parachuted down. Now, the whole descent lasted about 2.5 hours. I'm just going to play you about the last 30 seconds. And what you're listening to are just the sounds of the winds buffeting the little spacecraft. And this is what you would hear if you were there riding this parachute down to the ground. So this is the only real sound that I'm going to play today, out of the wind. And that then marks the moment that Huygens became the furthest thing that humankind has landed a space, it's the furthest thing we've landed on another body in our solar system.
I mean, get your head around this. Drifted down through the atmosphere on a piece of fabric, and finally came to rest after 2.5 hours on a moon in the outer solar system. I mean, I'm always blown away by this.
Well, we just received the signal from the probe at Green Bank Radio Telescope, so we know that the probe has passed through the fiery entry in the atmosphere and all the parachutes have been deployed, so we're only waiting for the data now, so everything is okay.
We can look now at Saturn in the sky and know we've been there, we've made our mark, and the solar system has become a very much smaller place, and that is a very big thing.
We're in very good shape. Everything came back as it should. We've got the engineering in place, then we've started getting the science data in place. We have to turn the scientists to work on that now, but so far everything has been on the nail or better than on the nail. How do I feel? I feel over the moon of Saturn.
When I first saw the images from Huygens and the river-like structures on the surface, I thought, it's magic, wonderful, thank you, God.
It was a very emotional event. It was the day that humans had landed a device of their own making in the outer solar system. It was like living science fiction. And I've come to call this a grown men crying kind of day, because grown men were disappearing into corners to have their own little private moments during this event so that they wouldn't get busted by their colleagues being seen losing it because of the overwhelming emotion of the whole event.
It's really important to tell what's higher than what. What we see for the first time here is the third dimension. It's like looking at something with one eye and then suddenly opening your second eye. You can then tell that mountains stick up out of the plains, and you can tell how far they stick up out of the plains, which tells you a lot. You can tell that channels have cut down into other parts of Titan. You can tell that lava flows have come on top of channels or channels on top of lava flows, and that tells you about what happened first.
The landscape that Huygens arrived at is a series of low hills with some flat plains in between. Huygens began seeing this landscape as it just began to cross one of the large bright hills. And as it approached that hill, it saw an area of river channels which run down to a flat plain. It crossed that area of channels and a coast, if you will, to the flat plain, and descended down into a very complicated area of bouldery hills with some flatter areas. It landed on the boundary of a flat area in a rocky or icy plain, I suppose, where material from the hills had run out, been carried perhaps by liquid methane, and was deposited there.
It looks very much like what we see Earth to look like. You see bodies of liquids. Instead of liquid water, you see liquid methane, liquid natural gas. But you see lakes that look much like Earth lakes. You see channels that look like Earth channels. You see rivers. You see even large fields of dunes that look much like the things we see in Africa.
Once it landed, Huygens took, he had about an hour before he died. He took a few pictures, and here's one of them. But be careful. This is 15 centimeters. This is 6 inches. That red line is 6 inches wide. So these are not boulders. These are pebbles up near the camera, okay? And this is probably mainly ice. Some water ice, some methane ice, okay? Dirty ice. A lot of the solar system seems to be dirty ice.
I hope you can see it looks a little washed out, but here is the horizon in the distance, taken by 3 cameras looking 1, 2, and 3. So they're all put together in a mosaic. And here you could see these cobbles. I think we all still think they're made out of water ice. They're about this big.
Now, Titan is particularly interesting because it's one of the planets that has a reasonable atmosphere associated with it, and it contains at least methane, which we believe may have been one of the ingredients on some of the early, in the early primitive Earth. And there are also indications, other indications in the atmosphere of Titan that there is organic chemistry going on.
We have one image which seemed to capture what might be a volcanic eruption. That's important because in the outer solar system, planetary scientists consider ice a rock. You know, what a rock is defined as depends where you are in the solar system. In an outer solar system, ice is a rock.
So we all know Saturn can float in a tub full of water, right? Totally, it would float. If you could make a bathtub that big, it'd float. It's very low density because it has mostly hydrogen and helium, right? But a very small core, probably. But Titan is a larger density than Saturn, but much less than Earth. So we know because of that, it's got to have lots and lots and lots of water ice underneath.
Now, if we have a volcanic eruption on Titan, we have an eruption of magma. And if ice is a rock, that volcanic eruption is water.
And that's good for us. That's a good thing. We want water ice. Because if we can melt it and make liquid water, we are on our way because all those organics are sitting there waiting for water. you know. So that's a really good thing.
So we have evidence of magma chambers, which could be cauldrons of life-giving liquid water. How cool is that? And how counterintuitive is that? How science fiction is that? That one of the most interesting places to look for is a lava chamber or a magma chamber on another planet that could be a cauldron of life suitable for sustaining life. I think that's really, really exciting.
The ice will melt. I'm not sure if it'll all melt, but a lot of it will melt, and you will have liquid water. And so then you'll have liquid water sitting on the surface with all these organics in it as well. And
Earth-based data that tend to rule out the possibility of high surface temperatures and therefore rule out life. But I'll leave the door open a crack. And I will certainly agree with you, my data do not have much to say about the surface temperature.
oh, probably from oh my God, I'm blanking on the first name, of course. Do you know? Yeah. Oh, why did NASA pick the name Cassini? And I should definitely know this answer. So I know for Huygens, is it Christian Huygens, right? And Cassini, you know the answer. Go ahead.
I think so. It's an Italian astronomer, and Galileo named the Cassini moons, I think.
Well, the
Cassini stars or something, but anyway, Galileo referenced Cassini as his association with Jupiter.
So Galileo, the Galilean moons on Jupiter, of course, Callisto, Europa, and not Enceladus.
To learn more about this imaginative career, call the Art Institute at 1-800-243-6700. That's 1-800-2.
I'll Google it with my phone. It's a good question. I hope the project doesn't witness me not knowing that answer.
The gentleman. Yeah.
It probably does.
Included in this image of Saturn are actually 4 satellites. 3 of them show up quite readily: Tethys, Dione, and Rhea. And this is the shadow of Tethys up here. But if you look very carefully, you'll see a little bright spot right here. That's Mimas, and its shadow is seen up here.
I've seen enough instances where nature imitates art, so I'm going to keep my fingers crossed with what Cassini discovers at Iapetus.
We've discovered a great many things about these moons. I can't say everything that we've found about them, but we have returned some spectacular pictures, and I can quickly show you those.
Here's another view of Dione. Okay, taken at very high phase angle as the sun was either rising or setting, I don't remember. And then here's a close-up of that. Okay, now I don't know about you, but this calls out for an astronaut, doesn't it? Don't you want to see an astronaut walking across the surface of that? Actually, you wouldn't be able to resolve an astronaut because the smallest pixel here is about 100 meters, so that's about a football field across. This is actually a very big, very large crater. And then here's our Death Star moon, Mimas. Okay?
A very, very large crater on one face of Tethys, a face that was not seen by Voyager 1. The crater is huge. In fact, it is the largest crater so far seen in the Saturnian system. It's about 400 kilometers, that is something in the order of 300 miles in diameter. The central peak is caused by the rebound of material up from the center after the impact, and then as that central peak slumps back down, it pushes up the mountain chain or the mountain ridge that surrounds the impact crater.
We have found some fantastic geology on Iapetus, as you can see. This is the moon that's half black on one side, half white on the other, half black and white.
Half of Iapetus appears as dark as asphalt, and the other half is as bright as snow. When Cassini discovered Iapetus in 1671, he could only see the bright side. We had a better glimpse when Voyager 2 flew past in August 1981.
We are looking for a single explanation for almost everything, and that's because this is the first chance to look at it, and probably there is no single explanation, and there are different phenomena taking place. I'm focusing on what produces the dark stuff, and that may have nothing to do with what's producing some of the geological features that we're seeing.
Yeah, the thing we really need to constrain at are a lot of craters where we can see the floors if they're dark or if they're bright, and we just haven't been lucky enough to see it.
This is it. This is the highest resolution picture we're going to get of Iapetus in our lifetimes, probably.
Reporting from the interactive room at JPL, I'm Carol Ackright, NASA News Net.
This is Pandora. Pandora orbits just outside of the F ring. You can see it's large enough to have craters on. In other words, objects have hit Pandora. But if you look at the texture around it, it's quite smooth. So it looks like it's being coated with particles, and these particles are likely from the F ring itself, just coating the surface. And you can see some landslides here. It looks like some exposed material, landslides into the center of the crater.
A very exciting moment. It was like, this part of the mission was like a Jules Verne adventure come true. And it was just a remarkable moment.
I could chew your ear off for hours about Enceladus.
I've saved the best for last, and that is the tiny moon Enceladus, an icy moon of Saturn. When we put Cassini in a position to look over the pole in the direction of the sun, which is a geometry which highlights the presence of small particles, this is what we saw.
Well, this is the only picture I'm showing you tonight of Enceladus. This is that picture. They'd already seen some hints of something earlier on. So they found a spot they could get a picture of Enceladus with the sun behind it. So they're silhouetting it. And sure enough, when they did that, they saw these jets of stuff. Since then, they have flown through them. They did all kinds of spectroscopy on them, what have you. They know it's mainly snowflakes, water ice.
When we flew really close, we found that, yes, there was an atmosphere at Enceladus, and the camera found cracks on the surface of Enceladus, and there was water vapor coming out from the surface of Enceladus.
We're flying very close to the surface, just 50 kilometers above the surface of Enceladus. And then we fly through the plume. We just sort of grazed the edge of the plume last time in 2005. This time we're really plunging into the plume.
Here's another view of those icy jets. This is a backlit view similar to what you saw earlier in the Saturn image. You can see the sunlight shining through each of these jets. And we found in the particles that some of those were salty.
We have good compositional information about this plume, and we found that those jets are accompanied by water vapor, but also the particles are salty with a salinity comparable to the Earth's oceans, and that tells you they are salty water droplets that are frozen.
Now, Cassini has flown through this plume several times, actually several. Now it's something like 19 times. There's an instrument on board, there's two in fact, that can pick up material and tell what its composition is.
We'll really be tasting the plume, taking the material from the plume into the instruments on board the spacecraft and analyzing them.
Well, here I have a model of the Cassini spacecraft. And Hunter, maybe you can show us where your instrument is that detected the hydrogen.
Yes, Linda. The INMS instrument, the ion neutral mass spectrometer, is sitting on the fields and particle platform right here. And it directly samples the gas that comes in as we fly through the plume. Let me fly my spacecraft with the INMS pointed in the direction of motion of the spacecraft through the plume material, sampling the gas. This is how it happened when we were making measurements. It was about 8 kilometers above the surface, and this happened in October of 2015.
The geysers on Enceladus are actually quite a lot like Old Faithful geyser or other geysers in Yellowstone National Park that we're familiar with. In fact, the total amount of material coming out of Old Faithful in one of its eruptions is similar to the amount of material that comes out of the geysers on Enceladus.
So we've got this fire extinguisher here today to show us what the plumes really look like. And you can see that they jet out, and they really do jet out.
you can see how active Enceladus really is.
This is an interesting view. This is another Enceladus. This is a fountain at Versailles in their gardens there. And this particular Enceladus is a Greek giant, and he had a run-in with his grandniece Athena, and he lost. And so his fate was to be forever buried under Mount Etna. So I think here he's protesting a bit with this giant 82-foot-high geyser of water. Who knew in the 1670s that Enceladus would actually kind of be doing something like this?
Why do you think there's so much more water on Enceladus and so much more organic matter on Titan?
Okay, so Titan is bigger. First of all, if you have a body that's bigger, if it had any volatile material, for example, well, let me just say, it can retain an atmosphere. Enceladus probably is not big enough to retain an atmosphere. So Titan has an atmosphere. It could have been outgassed. I mean, the answer is how, your question is really how it got that way. Enceladus, you just got to remember, Enceladus is tiny. It's really tiny. I guess I forgot to mention, the reason why it is the way it is because it's being flexed by a resonance with its next door neighbor, two satellites over, Dione. So it's got tidal energy that's being forced into it and has been for as long as that resonance has been in play. And that is what has melted the water and created the ocean. And then the organic material, I say let's take it as ground zero. The organics are everywhere. Really, they're everywhere. So, they are there on the ocean, in the ocean of Enceladus. The question is, have they done anything interesting?
People have searched on Mars for water. They've searched on our moon to be able to find water as well. What we didn't expect to find was there was water filling the Saturn system, and there's essentially water everywhere.
Those particles escape Enceladus and go into orbit around Saturn and form the E-rings. So we had found what was forming the E-ring, which had been discovered around Saturn in the 1960s.
We have had the scientists studying these plumes specifically in support of exactly the question of how risky is it to be flying through this part of the plumes. And they've come back consistently and unanimously to say that the particles are very small, micron-sized particles. None of the big particles can get lofted by the plumes to be as high as we're going to be. So the scientists are repeatedly assuring us that environment is just not a threat.
If NASA gave you $1 billion to go to Enceladus and figure out if there are microbes there, do you or other Earthlings know how to do that? Is anybody planning to do that? How do we do that?
Good, that was good. Yes, we are planning to do that. But NASA's not going to give us $1 billion. That's the bad news. The good news is we are planning it. There's various ways. Well, first of all, okay, you gave me the opportunity to say, I'm undoubtedly going to get some people upset, but I have to say it because it's the truth. Enceladus is the best place to go. Okay?
Chris, do you think there could be microbes or even shrimp in the ocean on Enceladus?
Why, that would be wonderful, Linda. But we haven't discovered evidence of organisms on Enceladus. But I'm encouraged by the geochemical data, which could allow for this possibility.
Mark?
Why do you say it's not possible to land on Enceladus?
Oh, just because.
On Titan?
No, just money. It's, the bucks. There's no bucks. It's a lot of.
Maybe you can drum up some excitement about Enceladus, a landing on Enceladus.
Well, I'm excited about it. Are you? Well, then, okay, go for it. Get us some money.
Bob Saget here, and this is our $100,000
premiere movie, The Woman Who Sinned, Sunday.
Voyager's 11 scientific instruments probed deep into the atmosphere of Saturn and gave us an unprecedented view of those incredible rings. The rings are sun-reflecting icy objects, ranging from boulder-sized to small particles that whirl around the planet at very high speeds.
This is a close-up of two views, actually, of the rings, an image and then a mirror image as the imaging instrument stepped back across the rings.
And so that means that by the time it got there, it was absolutely screaming by, and we had to slow it down, and that's shown in an artist's depiction here, what we call the Saturn orbit insertion maneuver, when we burned more than half the mass of the spacecraft at launch, which was fuel. We burned it in order to, we didn't actually slow down the speed, we slowed down the acceleration so that it could basically drop into orbit around Saturn. And so this maneuver brought us closer to the rings than we had ever been before. We'll ever get again, very likely never be as close as we were during this maneuver ever again in the course of the mission. And so the scientists for years were clamoring to be allowed this opportunity to take data when we were cruising over the rings. And that's in fact what we did. We collected a beautiful collection of images of the highest resolution we've ever had on the rings. And we saw many things. I don't have the time to show you all of them. One thing we saw a lot of was waves. I was stunned at how sharp and detailed and clear these images were. We saw the edge waves in the inky gap just sticking out like crazy. I mean, you could see it easily. That was the one picture where I said that I thought my team members were pulling a trick on me, because I was over in one building at JPL with everybody else getting ready for the press conference. My team members sent me some pictures, and I bring them up on the screen, and I thought, okay, this is somebody's computer simulation, and they're playing a trick on me. They just think this is a big joke that I'm going to get up and show this, and it's not a real picture. So I call over to building 264 where everybody was. I called 3 times, and I said, are you sure this isn't a computer simulation? It just doesn't look real. Come on, did you guys play a trick on me? No, it's a real picture. So suffice it to say, we were blown away. There were lots of things we discovered in the ring pictures then and since, and it's been like that with Cassini. It's almost like never-ending news.
It's a fantastic experiment when you think of the fact that the ring system, the distance from the inner edge to the outer edge of the ring system is tens of thousands of miles. It's comparable to the distance around the Earth. Yet we will measure detail there at the size of a city block.
I think we can say that our eclipse data, just as we go behind the planet, just at the end on the right there, are consistent with other analyses that imply that the rings are centimeter size.
30 feet thick. Now imagine. And the inner rings are only about 15 feet thick. The outer A ring, the big bright white one, about 30 feet thick. 170 miles in diameter. Are you getting impressed? I hope.
That makes them no bigger than about 2 stories in a modern day building. So they're very thin, despite the fact that Saturn's rings are across, they're about 1 light second. And in fact, I'd love to add this statistic because I think it's marvelous. If you took all the mass in Saturn's rings and recomposed it into a moon of the proper density for the Saturn system, it would be no bigger than Enceladus.
The rings, of course, are what make Saturn the icon among planets that they are. They are a tremendous visual spectacle. They would fit in nicely between the Earth and the Moon, just one into the other. And they consist of countless colliding bodies composed of water ice, ranging in size from small houses or small apartment buildings, actually, all the way down to the finest talcum powder, screaming around Saturn at 20 to 40,000 miles per hour, but only very gently jostling one another, millimeters per second.
The rings are composed of huge chunks of ice. At close range, they appear as an asteroid snowstorm.
The A-ring is a little bit more transparent, is punctuated by gravity-driven features that are driven by the gravity of orbiting moons. And now with Cassini, after 10 years, we've come a very long way to knowing exactly what causes all this structure. The B ring is where most of the mass is. That's the ring that casts the darkest shadows. We were really perplexed about what caused all these features in Voyager days. We have a pretty good understanding of it now. At least we think we do. This is the most diaphanous ring of the main rings. You can easily see through it. It's characterized by these plateaus of higher than average concentrations of particles, but otherwise it's very, very thin. And the A ring is the ring that every feature you see in it is due to a gravitational resonance with an orbiting moon.
Here are the rings. This is the F ring. I'm not going to say anything about that, unfortunately. We don't have time.
Here's the outer edge of the E ring. This is the F ring. I'm not going to say anything about. We've seen dozens of these in our images, and from that we can infer the presence of millions of them. There are lots of small moonlets in Saturn's rings that are way bigger than the largest particle of any number and that was, like I said, the size of small houses.
If you could hold a ring particle in your hand, what might it look like? Well, it might look like a fluffy snowball with very fluffy, tiny particles on the outside, but maybe there's an icy, rocky core on the inside. Most of them are really small. Some of them the size of dust particles or like little hail particles. A few of them snowball-sized, and then a very few maybe even mountain-sized.
Cool. You had a picture of the ring particles.
That was an artist's conception.
How close were you able to observe the actual appearance of ring particles?
Oh, you'd have to be really, really close to do so, to see them with a camera that had our kind of focal length. It's not possible. We couldn't get that close to the ring.
This, of course, is a computer model. Saturn is here. This is a model of the rings. Are you with me? Isn't that something? Let's see if I can do that again for you. I think I can. I think I can. So when we started, that was when the comet went by. And this is years and years of history. This is as it goes around and around Saturn. Okay, you with me? Published in two publications 10 days ago, March 31st. And these are peer-reviewed, reputable publications. I'm going to let you read this one.
We didn't see that in 1982, that it was one way and 83 another?
So what?
We didn't notice the change from 82 to 83?
It turns, that was in the paper. It turns out that what was it now? We didn't have any spacecraft up there, then to look. And Saturn was behind the sun. It was not at opposition. And so we couldn't see it anyway with ground-based telescopes. So whatever happened in 83, we don't have a clue.
Yes, over there.
Hi. In the artist's conceptions of the rings, it showed like each of them as sort of a large boulders of ice, sort of separate from each other. But when you show the picture of the edge of the B ring with the large mountains, ranges, and stuff like that, it looked like a solid ring. Is that true or not?
Okay, so first, that artist's conception, I always mean to update it, and I don't know, I'm sure someone's done a better job. That's not really what the size distribution looks like. I just want to take this opportunity to correct this.
Okay.
There's fewer big particles than small particles, but they are all in a plane, pretty much all in a plane. And whether or not it looks in the artist's depiction, whether or not it looks like it's solid or really dense or not, depends on whether or not the artist was thinking that he or she was painting the middle of the B ring where the particles are very densely packed, or so much so that they almost act like grain in a grain silo, or they're painting the C ring where the particles are very underdense. And as I said before, in our pictures, we are so far away that you can't resolve individual particles. So it will always look like a faint sheet of something.
But there's no part of the ring that's completely connected all the way around.
All the rings are completely connected all the way around.
But like solidly connected, not.
There's no solid, solid like a. Like what? Like a washer? Nothing like that.
So the mountains on the edge of the B ring are not like connected in
They're
any
not
way.
Mountains in the sense of being a contiguous mass. They
Right.
are. Think of them as piles of rubble. Rubble mountains made of rubble. Mountainous piles of rubble. That's
Right.
it. Okay.
Okay. Thank
So
you.
you could almost play a game of, I'm sure some daring guy would want to do this. Get in his shuttlecraft and try to
Mountainous walls of rubble, 2.5 miles high, above a ring that is only 30 feet thick. They would look, for all the world, if you're close to the rings, they'd look like they stretched on into infinity and coming upon a wall of rubble, you know, several miles high. And it would look to you like this sheet of debris was stretching to infinity, it would be so large. And you're flying along, and you're flying along, flying along, and flying along, and flying along, and eventually come upon a wall of rubble 2 miles high. You know, that should go in a science fiction movie. And a good friend of mine who's a space artist did the next best thing, and he put it on canvas. And I'm hoping that someday we actually get to do this. Anyway, Michael Carroll, a space artist, put it on canvas. And so I am hoping that someone someday actually gets to do this. Okay, so that's my idea for how rings come about. I'm just having a little bit of a problem getting it published.
The view here is tremendous. This is a real-time simulation of what we would see if we were riding along next to Cassini at Saturn right now. This is a simulation, an application we call Eyes on the Solar System.
This application is really cool. It has a full model of the spacecraft and a full model of the Saturnian system. So right now, the reason why we're doing it at this point in time is the spacecraft is flying through the outer edges of the rings. As you can see in that picture right now, you can see the rings and the spacecraft flying on the outer edges. So that's what's great about this, is it shows the orientation of the spacecraft and the orientation of the entire Saturnian system right now.
So cool.
The spacecraft will pass through the ring plane at Saturn, and this is probably the most dangerous part of its journey. Even though the spacecraft is going by Saturn outside of the 3 visible rings, the 3 rings that we can see from Earth, scientists are quite sure that there is a great deal of material which lies outside of the outermost visible ring, the so-called A ring. Well, Planetary Saturn is going to be going through that, and it will take less than a second for it to penetrate the ring and move through it.
The flyby is going to be such that we will, be irreversibly entering into Saturn's atmosphere, and at 30 kilometers per second, the spacecraft will be destroyed almost immediately, nearly 4 days after the flyby. Thus, the end to an incredibly glorious exploration of the Saturnian system, a legacy of science and science data and engineering achievements that will, I don't believe, be duplicated for a very long time, and I think a wealth of information for generations to come.
After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1. So here's what one of those, if you were sitting on Cassini, here's what you would see. To go from pole to pole takes about an hour. Just remarkable. I could watch that all day. We've used up most of our fuel that we use to control us as we fly by Titan, make our corrections to get us to our next destination. And when we got to Saturn in 2004, we used up half of it just to get into orbit. And since then, we've been using that fuel. And so now we're out of gas.
At launch, Cassini was nearly 6 metric tons at launch, but more than half of that was fuel that was expended in the Saturn orbit insertion maneuver.
You don't want to end a mission with a full tank. In fact, you want to end the mission with a completely empty tank, and right now we are almost completely empty. So the possibility of a controlled landing on anything would be absolutely out of the question.
By the end of the mission, we'll have 127 flybys of the giant moon Titan. And Titan is like a giant rocket engine. Every time we fly by Titan, it's like expending almost as much fuel as we spent to go into orbit for Saturn orbit insertion. Cassini weighed 6 tons, and about half of that was fuel that we spent, about a third of that, just to go into orbit around Saturn.
We've got about 36 kilograms of hydrazine left. Those are the little thrusters. And that's about where we wanted to be to finish up, because we'll use a lot of hydrazine. We use hydrazine every day to keep the reaction wheels spun to the right place, and then we also use them. We'll use them for the Titan 126 flyby when we go by at 979 kilometers. So we'll use about 10 to 15 kilos of that 36 that's left. And I'm going to fudge Todd's numbers here a little bit, because this is the big question is the fuel, the bipropellants, the monomethyl hydrazine and the nitrogen tetroxide. There's about 10 plus or minus 20 kilos of the fuel left, and that's the one that we're worried about the most. And we could be out today, we could have 30 kilos. The oxidizer's a little bit more. The oxidizer's running about 25 plus or minus that same 20. And so there's no more main engine maneuvers planned. We may need one at the end, but there's no more main engine maneuvers planned. We are doing maneuvers prior to T126, 3 days before and 3 days after, and hopefully that'll be done on hydrazine.
Yes.
What's the expected lifetime of the Cassini?
The Cassini what?
Imaging. How long is it going to last? What, run out of power or fuel or navigation?
Okay, so the real limit, you know, is politics. It's how much money the American Congress wants to give us to continue going, literally. Fuel is a precious commodity. We're planning the extended mission now, so we'll almost certainly go through 2010. And then after that, we'll plan through 2012. Almost certainly by then, our budgets will be way down. There's nothing on the horizon that looks like it's going to limit us mechanically, electrically, functionally. It's just how long they'll provide funding for it to go.
Time is 9:03 and 40 seconds. Right now, 20 more seconds. And we will be able to confirm the spacecraft has survived. 15 seconds. 3, 2, 1. The Pioneer Saturn spacecraft has survived the crossing of the ring plane.
Our micrometeoroid detector on the spacecraft received 2 hits. Now that is the maximum number of hits it can achieve in an 80-minute period. So it could have been quite a few more hits than 2. So there's no question we did go through a region that has some debris in it.
But now we're coming to the end. As it runs out of fuel, the things that it can do are quite limited. At least we thought, until we decided on a new approach, a grand adventure, new discoveries that we can use this system to make. And we call that the grand finale.
Now, Cassini has one last daring assignment.
During one experiment, scientists watched a star come out from behind Saturn and go behind the rings. They then measured the amount of starlight 100 times a second as it blinked on and off.
And here is a little video that we've put together that I hope you'll like, that gives you a little overview of what to expect.
On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
Okay, so first of all good things must end. And we couldn't go on forever spending NASA's money because there are other missions that are waiting to start, and they're good missions and they have to happen. So we made a decision on the Cassini project years ago that we would do the following. We arrived at the height of southern summer, and we thought it would be best if we got to at least the height of northern summer, because that means between the two hemispheres, we would have seen the full seasonal cycle on Saturn. We don't have to wait there 28 years to do it. 14 years is adequate. We see the southern hemisphere go from summer to winter. We see the winter hemisphere go from winter to summer. The height of northern summer is going to be September 2017 or thereabouts. Since we had planned that as a termination point, that determined how much we utilized the spacecraft, the rate at which we utilized the spacecraft resources in between. We're 10 years into this mission. It has already been the most scientifically productive mission, planetary mission that's ever been flown. We could take up libraries with all the information we have found out about the Saturn system.
There is a question I suppose we've been asked many times is, why are you doing this? You've got a discovery machine that's performing flawlessly. What's going on? Well, the short answer, and Jim alluded to it, is we're out of propellant.
So anyway, that was the decision, and I forget, how are we going to do it? Well, we're going to send the spacecraft, if it doesn't do it on its own, by running into a ring particle or becoming unstable on its own, we're going to send it into the atmosphere of Saturn. And people say, why don't you do something else? Why don't you leave it there? You could use it for A, B, and C. But since we have two bodies in the Saturn system that are of great astrobiological interest, Titan, because it's the only place we know of that's got organics on the surface, and Enceladus, because it's the best place in the solar system to go searching for life because it's easy to sample. We don't want to mess it up by accidentally, even if it's a remote chance, of seeding it with organisms that could still be on the spacecraft. Seems extreme, but it's just, it's not a big deal to do, and so that's what's going to happen to Cassini.
How were you able to prevent that when you landed Huygens probe on the surface of Titan?
I think the key difference between those is that Cassini is powered by these radioisotope thermoelectric generators with plutonium on board. And so to access the ocean on Enceladus, you'd probably have to melt through some ice. And with the heat from that plutonium, that might be a possibility. The Huygens probe had batteries and it had some small RHU heaters. And also, when we landed on Titan, we didn't know about the methane lakes. We didn't know that Titan also had a global ocean. We didn't know about Enceladus. So a lot of things, like as Earl said, Cassini is kind of a victim of her own discoveries.
I see. Thank you.
Let's bring back one of those clips, please. We are going to dive into the gap between the rings of Saturn and Saturn's atmosphere, a place no spacecraft's ever gone. At that velocity, oh, by the way, we're going to be doing it from 1 billion kilometers away. It's all being run from right here. Just another stunt.
The grand finale, it's going to be 22 orbits, about 6 months. What do we hope to accomplish in that amount of time?
We hope to accomplish a lot of incredible science, things that we have never been able to do before with the Cassini mission. To be able to do this engineering, to thread that needle between Saturn and its rings, is really challenging.
The grand finale is a series of 22 orbits where Cassini dives in between the innermost ring and the top of Saturn's atmosphere, almost an inside passage, very close to the planet.
What we learned about Saturn during that encounter and during the months that preceded it have really rewritten the textbooks on Saturn.
That has essentially rewritten the books on Saturn. It is just a phenomenal achievement. Cassini's legacy is absolutely assured. We are in the books, guys. It is just there. But The best is still yet to come, perhaps, but we are certainly going to provide more excitement.
If we started with a small book, a little novella that was about Saturn, and indeed largely imagination, we now have a solid 3-volume Baedeker guide to Saturn. But in the end, we're going to have an encyclopedia. In the end, we will have 100 books maybe.
The science we're going to get in the grand finale is like no other science we've gotten in the mission. We've never gotten this close to Saturn before. In fact, no spacecraft has gotten this close to Saturn. And that allows us to make measurements that you just can't make when you're orbiting outside the rings.
So, the science. I love the engineering of all of this, but really the engineering is all in it because of the science. And this is just some of the unique things. You've seen what Linda showed already, and it is phenomenal. And we're going to continue to do some more of that even while we're here.
We have some incredible science that will come back during Cassini's grand finale orbits. It includes gravity measurements of the planet itself, revealing the interior of Saturn and the depths of Saturn's winds. Then we have the magnetic field measurements. Perhaps that will give us the length of Saturn's day and help us understand how the field is generated inside the planet. We'll get the mass of the rings for the first time, as well as a direct measurement of their composition. Incredible pictures of the rings and looking at the North Polar hexagon, direct measurements of the particles and the radiation belt in this region, a whole host of unique science in the grand finale.
But these are opportunities that we will never, ever get any other time. Saturn internal structure, magnetic fields, and gravity. We'll actually be able to determine for the first time the mass of the rings. By flying in between the rings in Saturn, we can get a sense of where they, which one's which. And that tells us something very fundamental. Believe it or not, we don't know how old the rings are. They could be a couple 100 million years, they could be 1 billion years. There's a big argument about that, and very, very intelligent people on both sides of the case. We think we can help with some of these measurements.
The grand finale not only provides really incredible science, but it also helps us satisfy a planetary protection requirement. We're protecting the tiny moon Enceladus as well as Titan.
I think Cassini has left us with humankind's presence at another planet for 13 years, seeing things that we had never imagined seeing, and at the same time sharing that with the entire world and opening up vistas for the next sets of missions.
This is a model of the Cassini spacecraft, and this right up here is our high-gain antenna, a great big dish. And if you notice, almost all of the instruments, if you point it in the right way, are shadowed or shielded by that antenna. So first time in, we're going to go behind the high-gain antenna, having it shield everything we possibly can. Of course, the magnetometer's hanging out here, and they're on their own. But everybody else, everybody else will be back behind the shield.
Those decades of Cassini have flown by, and now here we stand on the brink of the grand finale. In so many ways, the grand finale is like a brand new mission. We're going to a place and obtaining data with the Cassini spacecraft we could only obtain in doing it this way. In fact, I wouldn't be a bit surprised if some of the discoveries we make with Cassini might be the very best of the mission from these grand finale orbits.
The spectacular ending, the grand finale, going out in a blaze of glory, is a phenomenal conclusion to a chapter in humankind's exploration of the planets. Just a chapter. The book is not complete. There's more to come.
So I think we can, in fact, replace the God concept, that is, the God as the explanation of all things natural, and I think, in fact, we've already done it. It's just a matter of developing a socially appealing way to get the word out to everybody.
I love knowledge. You know, to me, knowledge is power. It's so empowering to know the truth and to really understand something. Boy, when you understand, when you come to study something and you come to understand it, you know, even if it's just a little discovery that you make and you come to understand it on your own, it feels, it's like the greatest high.
There is a lot more to come.